So I have a 0.2 kilogram mass. This is the spring we dealt with yesterday. So I have a 0.2 kilogram mass that is at rest next to a spring that is in its relaxed position. The spring has a spring constant of 20 newtons per meter. A 0.6 kilogram box, sliding at 1.5 meters per second, collides with the first box, sticking to the first box, if you will. The system comes to rest. What is the maximum compression of the spring before it springs back? And how long does it take for the spring to compress after the collision? But question number 1 is old school, right? So there's the collision portion of this, which is a perfectly inelastic collision where 0.6 times 1.5 is going to equal 0.6 plus 0.2 times whatever the final velocity is after that collision. Yes? Can't hear you. No. Momentum is just mass times velocity. So we're good here. This is what we have. Now, this does not conserve energy. Folks, I think you should hear me. This doesn't conserve energy. Energy is lost during the collision. But remember, the collision occurs instantaneously. After the collision, you basically have one object moving at whatever this velocity is. And from that point forward, the kinetic energy that the two-box system has together will be converted to potential energy, compressing the spring. When the boxes stop moving and all the kinetic energy is gone and been converted into potential energy, you're at the maximum compression of the spring. How long does this take? Well, I don't need that. The oscillating parameters of a spring mass system aren't related to the amplitude, the speed, or any of those things. The oscillating parameters, the thing that controls it, are the mass and the spring constant. That'll get you the period, which is 2 pi times the root of m, which has to be the entire mass, over k. How much of an oscillation do we observe going from maximum velocity to maximum displacement? That's what that handout was about that I suggested you print out. It's right on there. How much is it? It is 1/4. I want 1/4 of the oscillation. Now I get you haven't done this before, but do you understand that I'm not asking very much here? This is a lot of the way in which these problems tend to be phrased. Let's try another one. All right, a guy is running away from another person. In order to get free, he grabs the 20-meter long vine and swings across to safety. Safety happens to be 2 meters higher than he is now. He's hopeful that the person pursuing will fall down into the gorge because there'll be no string for them to grab. How fast is he running? Actually, I'll ask that different. What minimum speed will get him to safety? And 2, how long does it take? I'd say that, again, low threshold for problems we've already done. I have to choose a method to do this. Is the guy changing height? It seems to me that I'm being steered towards energy. I think what would drive it home is what I'm being asked to find Energy's really good at talking about displacements and speed. Am I being asked to find one of those things? Seems like energy might be a good thing to look at. Is he currently at the lowest point in the problem? When he makes it to the highest point, is he stopping? I think so. Minimum. The minimum speed necessary will get him to 2 meters, and that's it. So I'm thinking gravitational potential energy here and kinetic energy here, and that's it. That's all question number 1 is asking. First semester physics. But question number 2, how long does it take? Is energy a good predictor of how long something takes? No, energy really can't tell us much about time. Power can, but there's nothing here about power, and nothing that involves power. So I think we're probably looking at another way. But there is something that's all about time, isn't it? It has to be simple harmonic oscillators. They are all about time. And considering that yesterday we spent a whole bunch of that time figuring out that the period of oscillation of a pendulum is 2 pi times the root of L over G, this seems like the way to go since L is 20. But how much of a period do we use? What is from equilibrium to max displacement? Again, that's why I had you print that thing out. Put on there things that are important. In this case, a spring mass oscillator and a pendulum share certain principles. Maximum displacement is here. One oscillation is from there back to here. So from this point to this point, how much of an oscillation? 1/4. So 1/4 this time. Same problem. In fact, almost an identical problem. I was hoping that you would redeem yourself. Yay. Did we need the mass of the guy? No. Do we need to find the velocity of the guy before we could do part 2? No. In fact, we didn't even need the 2 meters, did we? Luckily, when I walked around, I did not see anybody with a 1 minus cosine theta on their paper, or else I would have been more frustrated like I was 3rd period. Because at least you realize either, or you don't know what that is either. But if I'd asked for the angle that this made, that would have been different, right? Do we understand that could be the next question? There's no reason why it couldn't be. This object, some random thing, has a moment of inertia I, has a mass of m, and let's say that its center of mass is located right there. The x marks the center of mass. In fact, we're going to fix it in place at a pivot point here. And I'm going to draw an arrow from the pivot point to the center of mass, and I'm going to say the length of this arrow, x, is the distance from the pivot to the center of mass. If I take some random object and set it into uniform circular motion, what am I saying? If I set it into some kind of oscillatory motion, I want you to be able to determine, theoretically, if that object is in actual simple harmonic motion. So again, I'm trying to tell you what to do. I've drawn the object. We have identified that this object will oscillate. We grabbed a random object, we put a pivot point on it, allowed gravity to demonstrate that it would oscillate. We saw that the oscillations appear to be harmonic. They appear to occur in a regular way. So now you need to quantify it theoretically, which means you're going to need to identify how the forces may be causing a restoring force. So, can you draw in on this picture where you believe equilibrium will be? I hope that you all draw in the same thing, because it'd be nice to know that all of you are paying attention. I'm thinking probably something like this would be the equilibrium position, because downwards is this way. All right, so if that's the equilibrium position, how are you measuring displacement? I'm going to measure it as an angular displacement. I won't measure it as a linear displacement. like this, because that green line is not the line that the object would actually travel along. If I wanted to measure it as a linear displacement of, say, the center of mass, I'd probably have to draw an arc length. This is you establishing whether you want to treat this from net force and talk about the motion of the center of mass of the object, or do you want to call this net torque and talk about the motion of the object itself relative to the pivot point? I'm thinking net torque might be the best way to go, because it looks like it's traveling as a rotating object. So I think net torque is the right direction. Now, in order to do that, their next step is assuming it is displaced and is in some point in its motion. Identify the forces that act on the object. I suspect there are a couple. How many arrows did you draw? I think there's more than one force acting on the object. I think there's the clear and obvious one that probably most of you drew, gravity, straight downwards. There's probably another one. Because if that were the only force acting on the object, would it stay there? Something's keeping it from falling, so there must be some force acting at the pivot point. In fact, I think that force is probably acting somewhat at an angle on the object at the pivot point. I say somewhat at an angle because there must be a part of this force that is counter to the weight. But there also must be part of this force that is ensuring that individual pieces of my object are maintaining circular motion. And that is evident probably at the pivot point. Do both of these forces cause a torque? No. The one at the pivot point does not cause a torque. So now that we've established that the one at the pivot point doesn't cause a torque, you should establish a net torque relationship. Probably starting with net torque equals I alpha. Is that enough? Have I enabled you enough so that you are more able now and more capable? Can you finish? Your next step is to try and figure out what the torque would look like based on the parameters we have set for this problem. You should remember that torque is R times F times the sine of an angle. Can you use that? I'm spelling out all the little steps because I'm just watching people stare off into space. I don't care that it's 7th period. I intend to be shockingly condescending. Are you done now? What's R? X. Good. That's right. X to the center of mass. What is the force? What are we going to use for sine phi? We'll use theta. If you're paying attention, this angle and this angle have to be the same. So I think our torque is going to be X center of mass, mg, sine theta. Before we are done, you should identify an appropriate established direction for this torque relative to the displacement. Is the direction of the displacement into the board or out of the board? If I use the curl rule and I roll my fingers in the direction of the yellow arrow indicating displacement, it is into the board. So the displacement is into the board. So relative to into the board, let's say into the board is positive, 3-finger rule for the direction of the torque. Point your pointer finger in the direction of the torque arm and align your middle finger with the direction of the force. When I do that, torque is out of the board. Agreed? Right? Torque arm, force. That suggests that the torque is negative relative to the displacement. Now, we want to see if our net torque equation matches the established equation that is a simple harmonic oscillator. That will require us to replace alpha with a second order differential and then make comparisons to the standard equation for an oscillator. Step 1 and step 2. Does this match the standard relationship for an oscillator? Unfortunately, it does not. Our standard relationship for an oscillator says that the position function of the oscillator, when taken the second derivative of, will give you a negative sign, a constant, and the original function for the oscillator. But our function says that if I have a function for theta and I take the derivative twice, I will produce a negative sign, I'll produce a constant, but I will also produce the sign of the function of theta. So ours isn't the same. However, does our model suggest that we could choose the amplitude of oscillations and make the amplitude small enough so that we could use the small angle approximation? I think now we could. So for small angles, I think we could replace sine theta with theta and say this is an oscillator for small angles. The smaller the angles, the more like a simple harmonic oscillator this will be. Now, I've done all of that work for you. Can you just hop over the last step for me and you do this part, and I call on one of you and you tell me what the period of oscillation will be? Because that's the whole goal here, is to be able to derive the period of oscillation theoretically so that we can establish that indeed this is a simple harmonic oscillator. In my notes, the generic form of the period is 2 pi divided by c. Is that enough? Okay, you're struggling to find c. Perhaps I can help you with that. Couldn't wait. Hockey is a really fast sport, but physics is clearly a slower one. Shockingly condescending. Yeah, that's it, right? This is all there is? You take whatever the constant is, take the root of it. It is the angular frequency. I'm using C here because I don't want to get us confused. We know that there's also more to this. We can produce X as a function of t, and not x, theta as a function of t, omega as a function of t, alpha as a function of t. These are the other things that we can produce. I say we. I know I can produce them, and I know about 4 or 5 of you can produce them too, because we have generic functions that meet these needs. But again, I want to stop here. This is the real goal, for you to be able to take a situation that may oscillate and then apply to it. Look, the whole point, you get something, if it's a constant that's sitting here, this becomes C. So any place that we saw C in any other part of those equations, that's where it goes here. And for period, it's just inverted because it's 2 pi divided by C, so you just invert it. That's why I have it like that. Now, simple pendulum, physical pendulum. They have some differences. The period for the physical pendulum looks like this. A physical pendulum. That's what this is. That's what we just got. Now, you remember that a simple pendulum is a point mass at the end of a string, right? Do you all remember that? So a physical pendulum can be any shaped object that has a center of mass that is identifiable, and we pivot it about some point of the object. No matter where we pivot it, you would need the moment of inertia about the pivot point to calculate that for a physical pendulum. A simple pendulum, we say that the thing that is connecting the mass to the pivot point has no inertia on its own, that it pivots about the top point. The thing that's connecting it doesn't add inertia to the system, that all the mass is concentrated here, and we have some length string or something very light, a light rod or something like that, that holds it in place. What's the moment of inertia of this point mass as I've drawn it? ml squared. What's the distance from the pivot point to the center of mass of my point mass? What happens? Can you do it? The L's, one of the L's cancels. That's a good one. That happens. What else cancels? Yeah. It's got to happen that way, right? My other classes didn't appreciate what I'm about to say, so I can't assume you will. But I want to impress upon something, because I tend to think we focus a lot on the test. And I know it's 7th period. I'm looking at some of those dull glazes eyes over there. Can you just stop for just a minute and maybe snap out of whatever place you're at right now and be right here in the room? Because you done yet here? Because I don't have the time that I'd like with you guys to do this, but a simple pendulum, square root of L over G, sure. A 1 meter long physical pendulum compared to the grandfather clock's pendulum being 1 meter long. If I do the work here, where I is 1/3 ml squared, and x, the distance from the pivot to the center of mass, is L over 2 mg. I can cancel one of the L's. I can cancel the m, which is why I was going to be frustrated if somebody asked me for m. And do you also get that it's 2 pi times the root of 2/3 L over G? The reason I want to do it this way is to make it very clear. The physical pendulum that's 1 meter long oscillates faster. And that's because although it has half the torque, it has 1/3 the inertia. Now, as you guys pack up, I have 2 people who said they have standing clocks and a few people that had wall clocks. Have you looked closely at these clocks? Who has a floor clock, a grandfather clock? Have you looked at the back inside where the pendulum is and noticed that you can adjust the length of the pendulum? Weights are for adding energy to the system because energy is taken out of the system every time it moves the second hand. And it's for like the alarms and stuff. Why do you think you can adjust the length of a grandfather clock's pendulum? A question I want you to answer tomorrow when we come to class. The other classes have answered it already.